Yes, dear students, in this lecture we are here to discuss about the streamline flow, turbulent flow, critical velocity, and Reynolds number. These all things we are going to discuss here. So first, what we are going to discuss here means streamline flow. Streamline flow of liquid particles, which we are going to discuss here. So what is the streamline flow means? The velocity of all the fluid particles crossing the one point is nothing but remains same. No, that is called what? Streamline flow. So we can tell that if the velocity of all the fluid particles crossing the point remains same both in magnitude and direction. So generally we can say simply what we can tell means here ordered flow of liquid. So example what we can tell means example we can tell like calm flow of river. So generally if I take these are nothing but boundaries and here river is passing here like this. So in this river, if you observe here, no, at any point, if you check velocities of the particles, no, for example, I'm going to choose here this particle velocity v1, this particle velocity is v2, this particle velocity is v3, this particle velocity is v4. All the velocity values should be equal. v1 should be equal to v2, that should be equal to v3, that should be equal to v4. And both magnitude and direction as well. So direction also should be same direction. This is nothing but what we can tell streamline flow, which we can tell here. Next, second one, what we need to discuss means turbulent flow, which we need to discuss here. Turbulent flow. Turbulent flow of liquid, which we need to discuss. So what is meant by turbulent flow means we basically if the velocity of all the fluid particles, if the velocity of all the fluid particles crossing the point not constant means different speeds they are having. So one more point we need to discuss here. What that point we need to discuss means critical velocity. So what is meant by critical velocity means the velocity at which it is the velocity of the fluid particles at which streamline flow change into turbulent flow. For example, let me take one river is there here and some liquid is flowing like this. What will happen means let me assume one big stone or something else is there here. What will happen then this water tries to come over on that. So like this it will tries to come. This fellow will go here, this fellow will go like this, this fellow will go like this and will come like this. Here if you observe, no, velocities will be changing as well as in the direction as well as magnitude. This velocity of the particles is called what we can tell critical velocity, which we can tell here. The velocity at which streamline flow is converting into turbulent flow is called what? Critical velocity, which we can tell. Now we need to discuss about the Reynolds number. What does this Reynolds number? What does the difference we are going to discuss here? Reynolds number. For example, let me take one container we're having here, or one pipe, let me assume. One pipe is there here, whose diameter is going to be capital D. Liquid entering is nothing but rho density, and eta is nothing but coefficient of viscosity. Coefficient of viscosity. What is meant by this means I'm going to discuss in next topic, this one only. Viscosity. So, and Vc is nothing but critical velocity, which we know here. So what is the relation? How can we give? Means Reynolds number capital R can be given as what? Means d rho Vc divided by eta. Eta is nothing but what here? Efficiency, which we can write it here. So this relation we got it. D is nothing but diameter. Rho is nothing but density of the liquid. Vc nothing but critical velocity, where it will convert into turbulent flow. Rho is nothing but viscosity of the liquid. Opposition to the viscous force means nothing but frictional force in fluids, which we can discuss here. So here about R, we need to discuss few points here. So this R defines you about which type of flow it is, streamline flow, turbulent flow, or what, which type of flow it is. For example, note. First, for example, first point what we can mention means if 0 less than R less than 1000, R value lies between 0 to 1000 means that flow of liquid is called what? Means streamline flow, which we can consider. Second point, if R is greater than 2000 means what we can tell? Means that flow is nothing but turbulent flow. Third point, what we can conclude means if 1000 less than R less than 2000, so the value between 1000 to 2000 means, so what we can tell means flows unsteadily, we can names flows unsteadily. So it's neither streamline flow or neither turbulent flow. So unsteady flow, which we can consider here. But if 0 less than or less than 1000, no, value of the R value is less than 1000, no, that we can consider streamline flow. Value of R value greater than 2000, no, turbulent flow. Between 1000 to 2000, no, what we can tell? It's simply we can tell flows unsteadily, which we can name here. Next topic, what we're going to discuss means, as I told you, viscosity. We're going to discuss here. What is meant by viscosity? So, in simple name, what is meant by viscosity means I can tell that that's nothing but fluid friction. Fluid friction, which we can tell simply. So, for example, let me take an example to explain this. We're having here one surface. In this surface, what we're having means one liquid drop is here, like this. Liquid drop. To explain this concept, I'm going to cut that surface into, I'm going to cut that liquid drop into layers. This is the liquid drop, no? Liquid drop. This is the liquid drop, no? So that liquid drop we are going to cut into layers. This is first layer. This is second layer. This is third layer. I'm going to cut like this. 3 layers I cut it here. After cutting that, what I did means I'm just going to tilt the surface. Tilting the surface. See, if you tilt the surface, now what will happen means you will get like this, na? That liquid drop. You will get like this. Now, among this first layer, second layer, and third layer, which layer will move with high speed? Which layer will be touching with the floor? It won't give means. Since this will be holding this, no, first layer. So first layer won't move. So third layer speed will be high. Second layer velocity will be little less. First layer velocity will be still more or less, which you can consider here. So if I show you, if I tilt like this, no. So here you can able to observe 3 layers like this. First layer, second layer, third layer. 1, 2, 3. Whose speed is more means who is having topmost corner, topmost, no? That fellow speed is more. Since it is touching with the floor due to friction, so it won't move here. So if I take here now commonly 3 layers. So let me assume down one is not at all moving. Second one is going with velocity v. Third one is going with velocity v plus delta V, some extra velocity. Third one is going with high speed, no? 1, 2, 3. So it's very clear that V3 is greater than V2, that is greater than V1. Now, velocity gradient I want to check here. Velocity gradient. Velocity gradient. What is meant by velocity gradient means change in velocity upon x. Rate of change of velocity means what will happen? Velocity upon time. No? Velocity gradient. What is meant by gradient means something upon displacement, which you can call it as here. So velocity gradient means V final minus V initial. V plus delta V minus V divided by what I can call it as dx. Therefore, this fellow will get cancelled. What will happen? Let me write dv. So dv upon dx will get as. This is called what we can call it as velocity gradient. So generally, grade means what? Something divided upon distance or length is called gradient, which means del. So this viscous force is there, no? So generally, this viscous force is directly proportional to what means this surface area, this area, and it's directly proportional to what means F is directly proportional to what? Velocity gradient. Velocity gradient. So if you observe here, no, Fe directly proportional to A, and one more thing is what we are having, dV by dx. If you remove proportionality, no, Fe equal to what it means, eta into A dV by dx, you will get it, Nana. So this is nothing but what we can call it as means viscous force, and here eta is nothing but what we can call it as coefficient of viscosity or coefficient of fluid friction, which we can call it as here simply. Now F equal to eta into dA into dV by dx, we got it. Now eta value I want to write from this equation. So if you write eta value from this equation, what we can write here? Eta equal to F upon area will go to this side, means it will go to denominator, into dx by dV. Dx by dV is nothing but what we can call time dimensions. Force upon area is nothing but pressure dimensions. So eta equal to force upon area into dx by dV. So this can be written as SI unit. I can write like SI unit. How can you write? We can write like Pascal. Force upon area is nothing but pressure, no? Into dx by dV is nothing but time dimensions. If you want to check here, time. Sorry, 1 second. Let me show you with basic. Yes, you know that velocity is nothing but what you can write, displacement by time. So time equal to what you can write, dx by v. So dx by v is nothing but what we can write, time dimensions. That's why I'm writing here seconds. So Pascal seconds we can write it, or CGS unit if you want to write, no, CGS unit. That's nothing but what, poise second. And you know that 1 Pascal equal to how many poise? No? 10 poise, which we learned in units and dimensions. No? That's why 1 Pascal second is equal to what we can write, 10 poise seconds. If anywhere conversion is there, no, you have to go with this thing, 10 poise seconds, which we can write here. And if you observe, I need to mention the dimensional formula. If you want to mention the dimensional formula, no, here, so dimensional formula. So first, what we're having, pressure into, otherwise we write from this formula, F by A and dx by dt. F is nothing but what we're having here, m power 1, L power 1, T power minus 2 into dx is nothing but L divided by area is nothing but L power 2 into dv. dv velocity is nothing but what, Nana? L power 1, T power minus 1, which we are having here. L power 1 will be L power 2, will get cancelled with this thing. So when L power 1 will goes to numerator means L power minus 1. T power minus 1 if it goes to numerator means T raised to, okay, minus 1, 1 minus 1 let me cancel. So what will happen? T raised to minus 1 will be remains here. Therefore, simply what we can write it means here, a dimensional formula. Do remember, very important for solving the numericals sometimes by dimensional method. M power 1, L power minus 1, T raised to minus 1. They can ask you for boards also. Sometimes for NEET and CET, they can ask you directly dimensional formula of what? Coefficient of viscosity. What we got it? M power 1, L power minus 1, T power minus 1, which we got it here. We have, which we need to remember, Nana, here. Next, if you observe here, no, we need to discuss about one more law, that is called what means Stokes law. Stokes law. Stokes law is nothing but what means another form of viscosity. Stokes law is nothing but what we can call it as another form of viscous force, Nana. Viscous force that is given by what means, so they given like this, Fv equal to 6 pi eta Rv. 6 pi eta Rv, where R is nothing but radius of the object and viscosity pi is constant, V is nothing but velocity. So finally you can conclude this formula like this: Fv equal to eta into A into dV by dx, that equal to 6 pi eta Rv. Whichever the one useful, no, that one we are going to use the for derivations and for numericals also. Either thing which we can get use here. See, next, which concept we are going to discuss? Means we are going to discuss about terminal velocity concept. Terminal velocity. So here what we are going to assume is, let us consider an object of density sigma and radius r is moving in a fluid of density rho. For example, let me take free body for this concept which I told you, FBD. Free body diagram we are drawing. Let me take one spherical surface here, and here downward what will act generally? Weight will act. W equal to mg. So weight can be written as what we can write it here? Sigma Vg we can write it here. Weight can be written as sigma Vg. Now sigma into volume is how much? 4 by 3 pi r cube into g we can write it. How can you convert sigma into V? No doubt in that density is nothing but mass upon volume. Mass equal to sigma into volume, which we can write it here simply. Okay, fine. This is, since object is coming downward with an acceleration A, backward what will happen? The force of buoyancy will come, no, when it is moving in some liquid or fluid. Fb is nothing but what we can tell? Rho Vg. Rho into V value is how much? 4 by 3 into pi r cube into G, which we can tell here. And if something is going downward, now we learned about some more force, that is nothing but viscous force, fluid friction. If it's coming downward, no, frictional force will act which direction? Upward force only. So that's nothing but Fv. That can be written as 6 pi eta Rv, which we can tell Nana here. Now, what will happen means, note. So generally what will happen, we are just releasing this object, and generally initial velocity is how much? 0. So initially velocity is 0. As we go down, velocity will increases. Why velocity increases? We know that v square minus u square equal to 2as. U value is 0. Therefore, v is directly proportional to what we can write it? Under root 2gh. A will become g and s will become like height, how much it's traveling here. Since its distance is increasing, means what will happen? Velocity also increases here. But at one particular case, what will happen means, at one particular instant, for a particular value of v, the upward forces will be equal to downward force. One second. Upward force is equal to what we can tell, Nana? Downward forces. See, upward force is equal to downward forces means A equal to the acceleration can be written as what from generally Newton's laws of motion, sigma m. If upward force is equal to downward force means F net equal to 0. 0 upon m is nothing but how much? 0. Therefore, acceleration is 0. When acceleration is going to become 0? velocity should be constant. Therefore, velocity is constant. This constant velocity is called what we can call it as Nana? Terminal velocity. As we go down at particular instant, upward forces should be equal to downward forces, then F net equal to 0. F net equal to 0 means acceleration will be 0. Acceleration is 0 means velocity is constant. This particular value of velocity is called what we can call it as terminal velocity. How to find terminal velocity? So just now we written here terminal velocity means what? Upward forces equal to downward forces. Then equate that. So what we can tell here means, so we can tell like this, Nana. Forces acting F upward should be equal to F downward. You can see clearly in the diagram. Upward force is buoyancy force plus viscous force. Downward force is weight is acting. So mention those both forces here. So F upward equal to what you can write it here? FB plus FV equal to downward what is acting? Weight. FB is how much we written here? Rho into 4 by 3 into pi r cube times G is equal to FV, viscous force, sorry, plus is there, no? FV. 6 pi eta r v subscript T, that is I'm indicating like a terminal velocity, is equal to sigma into weight value 4 by 3 pi r cube times the G, which we got it here. Now I'm going to shift this term here, Nana. So if you shift this term here, what will happen? Let me check here. So if you shift here now, 6 pi eta r vt equal to here 4 by 3 pi r cube. If this fellow comes to RHS, 4 by 3 pi r cube common, Nana. G also common. Sigma and rho only remains. Here sigma having positive. If it comes this side, no, negative sign. We're sending this fellow to here. So what will happen? So we can write like this. 4 by 3 I'm taking common. 4 by 3 pi r cube. G I'm taking common. Sigma minus rho remains here. If you observe here, no. So cancel carefully. This pi cancel with this pi. And 1r will get cancelled, and r square remains here. 2 2 ja, 2 3 ja. So we required Vt, na? Therefore, Vt equal to what we can write here? Vt equal to 2 is there here. If these 3 comes here, no, 9 it will become 2 by 9. Here r square remains, r square. Here eta is there. I'm sending to RHS, it will go to denominator. Eta into sigma minus rho times G. G also remains here. Therefore, Vt equal to what we can write now? Vt equal to 2r square by 9 eta times the sigma minus rho into G, which will get it. It's nothing but what we got it. Terminal velocity relation, which we got it here. In terms of radius of the object, density of the object, density of the fluid, and G value is nothing but acceleration due to gravity. So if you want to plot the graph here, no, if you observe here, velocity versus r radius, if you draw here, no, velocity, terminal velocity directly proportional to r square. So what we can draw means, if you draw the graphs now here, terminal velocity versus r, so that fellow looks like what, Nana? It looks like x directly proportional to y square. We'll get a increasing graph like this, Nana. Our terminal velocity graph, if you want to draw, no, terminal velocity with time, oh, terminal velocity with time, if you want to draw, no, with time, we'll get a graph like this. So I'm taking one graph like this. Here what we are taking? Velocity, Nana. Here we are taking time. So what we have discussed, observe here initially. Initially velocity is how much, Nana? 0. As v is directly proportional to h, no, velocity will be increasing. At particular one constant, what will happen? Velocity will become constant. That is the graph which we have to draw here. So if you observe here, no, velocity value starting from here, increasing. At what particular instant, what will happen? Velocity will become constant. This velocity is called which velocity? Terminal velocity, which we can tell, Nana. This is the one which we need to understand. Nothing is there. You just have to balance upward forces equal to downward forces. Then cancellation should happen. Vt equal to 2r square by 9 eta sigma minus rho into G. Sigma for object, rho for fluid. It depends on the teacher how they are teaching. Here they can take some teachers rho. This can take sigma. That's why in the theory starting only I mentioned that. Let us consider an object of density sigma, fluid of density rho, which I mentioned here. You have to understand this point clearly. And this is for today's class. Please go and revise once again for better understanding. Thank you.